A struct, or structure, is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions, especially the kind of associated functions called methods, to specify behavior associated with a struct type. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key-value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template with particular data to create values of the type. The syntax period specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Debug trait can be used with #derive if all fields implement debug. When derived for structs, it will use the name of the struct, then a comma-separated list of each field's name and debug value, then. For enums, it will use the name of the variant and, if applicable, then the debug values of the fields, then. Clone is a common trait for the ability to explicitly duplicate an object. Differs from copy in that copy is implicit and an inexpensive bitwise copy, while clone is always explicit and may or may not be expensive. In order to enforce these characteristics, Rust does not allow you to re-implement copy, but you may re-implement clone and run arbitrary code. Since clone is more general than copy, you can automatically make anything copy be clone as well. Let's create a new file called some Struct. Through this we will learn how to create and use a module. Declare a struct in remote file and then use it anywhere in project. Learn visibility amongst modules. Let's create a new struct called some Struct. It should have a Boolean field called as active. But notice we are not using pub keyword anywhere. This will prevent us from using the struct outside scope. Let's modify the privacy of our struct. Let's make the struct public, but not its fields. We can see if we wish to access the field is active, we cannot. It is because the field is private. Let's change that for now. Everything works as expected. Let's derive debug for our struct. An implementation of composition over inheritance typically begins with the creation of various interfaces representing the behaviors that the system must exhibit. Interfaces can facilitate polymorphic behavior. Classes implementing the identified interfaces are built and added to business domain classes as needed. Thus, system behaviors are realized without inheritance. In fact, business domain classes may all be base classes without any inheritance at all. Alternative implementation of system behaviors is accomplished by providing another class that implements the desired behavior interface. A class that contains a reference to an interface can support implementations of the interface, a choice that can be delayed until runtime. In Rust, there is no concept of inheriting the properties of a struct. Instead, when you are designing the relationship between objects, do it in a way that one's functionality is defined by an interface, a trait in Rust. This promotes composition over inheritance, which is considered more useful and easier to extend to larger projects. The impl keyword is primarily used to define implementations on types. Inherent implementations are standalone, while trait implementations are used to implement traits for types, or other traits. Functions and consts can both be defined in an implementation. A function defined in an impl block can be standalone. The other use of the impl keyword is in impl trait syntax, which can be seen as a shorthand for a concrete type that implements this trait. Its primary use is working with closures, which have type definitions generated at compile time that can't be simply typed out. You can create an impl block for a struct in any file you like. This makes working with teams on a project easier. Let's say person A is implementing a functionality in file A and similarly, person B is implementing some other functionality in file B. Rust makes it easier for them to work independently and still providing correctness. Let us create a default function over our user struct. It will generate a fixed user for us. Self is the type of the current object. It may appear either in a trait or an impl, but appears most often in trait, where it is a stand-in for whatever type will end up implementing the trait, which is unknown when defining the trait. Let's use self keyword as a return type and return self from our default function. Everything works as expected. Let's impl our user struct in main file. For this we will create functions that will act as a getter and a setter. We will learn to use self as a function parameter. Having self as the first parameter is how Rust defines methods. It is just a convention that converts a function into a method, much like in Python. Functionally, self is analogous to this in JavaScript. With this we can use the period operator over our instance of struct. Everything works as expected. This was a small introduction structs in Rust. There is still a lot to cover, such as tuple struct. We will discuss about such topics in upcoming videos. If you haven't already, don't forget to like, share and subscribe. Thank you and visit again. Happy coding!